So instead, I have to refer back to my previous job, which was with ERM. And luckily, there's some of my former colleagues here in the room. So there's Ellie and Michael. Go find them. So the work I'll be presenting today is really work that we've developed at ERM, especially with my colleague Samar Ahmoud, who's now since also moved to Vale, and but David Cater's still there, and so is Nerys Walters here in this country. So anyway, so if you have any questions, you can fire them to me, but I'll send them on to them. The background picture here is of the Netherlands, and this is actually a site where we went to visit earlier this week, in northeast of the country, where there's magnesium salt production, and this is done by solution mining. So you can see here at the surface, there's just a couple of silos and a warehouse kind of thing, and then there's some pumps to pump water down and salt up and recover it that way. I think this is sort of the image of what I envision the mine of the future to look like, even in the sulfide space, if we manage to get there in terms of cracking the nut on in situ recovery of tightly held sulfides. Anyway, so the answer is yes. Let's start positively. Obviously, there's all kinds of legislation coming at us from all sides, whether it's legislation or clients requesting or companies themselves just wanting to be more sustainable. We want to move to a more circular economy. Yes, that's all well and good, but we still need the input of metals to get there. So first, I'll give it a little bit of a why and rationale of where we're going. Eventually, I'll give you a couple of examples of how we use data really to help forecast material behavior in mines. So first, can we transition away from fossil fuels energy? The answer is obviously yes. Do we need to produce a lot more metals then? Yes, we do. Are there enough in the ground? Yes, there are. Could we produce them with less negative impact on society and environment? Yes. Do we know how? Yes. And this is where we're getting to in a few slides. Is, can we get better at forecasting how materials behave, not just in the mining and processing, but also in the environment? Do we also need to change our behaviors? Yes, we do as well. So if I were to ask you, I've built a machine. It's the latest technology, but it sits idle about 96% of the time. Would you fund it? If I built a processing plant that sits idle 96% of the time, would you buy it? Yes. Someone who loves their car does. So we buy all these cars, and they sit idle on average. These high-end pieces of technology sit idle for 96% of the time. The other 4%, they're stuck in traffic on the way to the gym to ride stationary bicycles. So anyway, we just need to get a bit smarter about how we deal with our materials and be less wasteful. That's the point here. Now, how do we get there? Here's one more piece of rationale. Why bother? Well, historically, we've looked at projects, and we still do in some cases, where we just look at the grade and the tonnage. Is it there? Can we dig it up? Can we mine it? Yes. Let's invest a couple $1 billion and go at it. Then we start producing. So we have product and waste at the end. And the true risk involved and the true cost of producing metals isn't really known until we're in the production phase. And then if we're not careful, we might be stuck at the end of the mine life with a multi-billion-dollar liability if we haven't properly characterized the waste, tails, impacts. And we have all these liabilities on our books. And if you ask any of the major mining companies what it would be worth to them if they could relinquish half of their liabilities in assets that just sit there and don't actually generate any value, that would be a lot. I don't know how much, but it would be a lot. So what we're proposing here, and this is, it's a play on the ore body knowledge. So we've had this terminology where it went from geometallurgy to geomet to ore body knowledge. And then we say, well, if we're actually getting a bit smarter about using our exploration data to understand, to forecast how materials will behave in the process and plant, we add some data analytics to that, hence the ore body intelligence. So if we actually combine that ore body knowledge with analytics to really try and optimize a process even before we've sunk our development capital, then we could probably operate at a much tighter margin with greater value and lower risk. So what do we actually need to know in order to make this process happen? Well, the things that we generally collect. What do we actually need to know? Of course, that's different for each deposit, but in general, assays, lithology, alteration, oxidation, mineralogy, petrophysics, the things that you normally collect. Now, the only thing is to bring them together, to put them in a block model where they fit together. And I like this. The Mira geoscience have a way of, they call this the common earth model, which is essentially saying, well, there's only one reality down there. So our different aspects need to agree. If there's disagreement between your geophysical interpretations, your logging, and your geochemistry, then something's wrong and you need to fix that. So make sure your data is collected in a way that's QC'd and reliable, and that it holds together. Now, if you do that, you can build a block model with a lot more parameters than just grade. You can then use that to, inform your mine plan, blasting, loading, and hauling. And then from there, it doesn't stop because there's an ore stream and a waste stream generally. But as we talked about before, some of the waste could be upcycled again and, might be reprocessed, or, if it does go to tailings, could the tailings be reprocessed or repurposed? And you could still generate a lot of value out of that. And then what happens with the actual waste streams? Is there still an opportunity to use it for carbon capture? Is such as Bruce site? And anyway, you can read the case studies there. And when there's true disposal, what do you actually dispose of, and is it ready for closure? So you end up with a block model that's got a lot more components than you might be used to having. And in that case, you may have to do some separate geostatistical analysis to populate your block model and cross-validate that against each other. Now, if what is it worth to you to actually have things like, not just grade and byproducts, but also things like asset-based accounting we just talked about, or comminution cost indicators. How much energy, how much water are you going to be using, et cetera, et cetera. So a lot of that can be forecast from compositional data. So I'll give you 3 case studies. The first one is looking at clay contents in gold mine. So Dundee Precious Metals, they're happy to share this story. Worked on the Ada Tepe gold mine in Bulgaria, and they gave us this at first. Said, well, got 7,000 holes, almost 500,000 gold and silver assays, and we have a clay problem. Can you solve it? Well, not from gold and silver assays. We can't estimate clay content. But we suggested to just run a few fences through the deposit and say, let's do some remedial analysis. TerraSpec data, which is just a handheld infrared analyzer here. They come in different forms now. There's the Halo and you name it. But it's infrared reflectance spectroscopy, which helps you say a little bit about clay mineralogy. And then 4-acid digest multi-element geochemistry for about 2,500 samples. And to check the actual mineralogical composition, there was a set selected of 34 samples for quantitative XRD, which is a bit more costly and time consuming, but it helps us sort of check back the actual composition. So when we looked at the accelerated fraction data, so this is quantitative mineralogy, we realized that, yes, there's a lot of quartz in the system, obviously. And then there's kaolinite in the orange at the bottom. And there's K feldspar. So there's adularia in purple. And there's very little other aluminosilicates, which is important. So there's a little bit of illite mica and one sample with smectite. But other than that, all the aluminosilicates are either in kaolinite or feldspars, which helps because it makes it a little easier to do a predictive model for clay content. So you actually generate a kaolinite proxy by saying, well, let's look at this kaolinite spectral contribution. So how much of the spectrally active material is kaolinite, and you can measure that by from the infrared spectrum, and then we times that by the available aluminium minus potassium minus sodium, and there's a correction factor there to get to the actual kaolinite content. And when you compare that to measured kaolinite by QXID, we get a pretty good relationship. All right, so now we have a relatively coarse sampling of high resolution, multi-element geochemistry to project across the deposit. But when we do that, you can see that in the background in colors, that's the kaolinite proxy modeled. Our colleague Neris did that. And in the blocks, the gray blocks, you see the blocks that are ore grade blocks above 0.6 ppm gold. Now you can already see which blocks are affected by high kaolinite and which are not. And they managed to actually blend their problem away here. So even with this relatively coarse remedial sampling that we did, it was enough for them to solve the clay problem. All right, so that's one example. And that is not quite, we're not quite using the analytics yet here, the data analytics. The second one also, we're just, just basic modeling. So this one is about a epithermal gold deposit in the tropics. And there's a problem with arsenic and waste. There's a lot of arsenic, and a lot of that arsenic would go to the waste pile. And could we say anything about the 3D distribution of arsenic? Well, obviously, that's easy. So yes, you can just look at the arsenic concentrations in drill core. To our new colleagues at the time, we were just, CSA Global was just acquired by ERM. And our colleagues at in the environmental department, they did fantastic work, except that they were not 3D modelers in this sense. And they were really happy with this picture. So, well, we can do a little bit more than that. We can, for instance, generate a arsenic distribution model in 3D, and then we can, also we can also do the geostatistics on that and calculate it on the block model. So now we have arsenic distribution block model, which is helpful for understanding how much arsenic is going to, not only going to the plant, but also how much is going to end up in your waste pile. We did another analysis to also look at, what can we calculate the, how much arsenic is in saprolite versus fresh rock. And another neat thing about, generating a model like this, which the engineers are very happy about, is that the final pit shell, if you project the actual arsenic concentrations now on the shell, you can see where your hotspots are that you may have to seal for a closure situation if you generate a pit lake there, where might be sources of arsenic, seeping into that. So that's just helpful information. Now the key here is that the arsenic waste, arsenic-rich waste, the fresh stuff, when you oxidize it, arsenic has this nasty habit of being quite stable when it's fully oxidized, quite stable when it's fully reduced, but when it goes from one to the other end, it gets quite mobile, and that's when it's also most bioavailable and most toxic. So as long as you keep things reduced, it's fine. As long as you keep things oxidized, it's fine. But when you move from reducing to oxidizing conditions, you have a big problem, or the other way around. So here there's some shake flask extraction results from this particular project, where you can see that the fresh rock, when oxidized and shaken, not stirred, it actually produces quite a bit of arsenic in solution. So much so that if you have about 100 ppm here in the solids, you already start to exceed here the IC guideline of 0.1 ppm in solution. So that fresh rock, it contains like some nasty arsinosulfides, sulfur salts, sulfide, something nickel sulfur salt. Anyway, that stuff, it oxidizes. So if you put that on top of the pile, obviously you start mining from the top. So you start mining the oxidized stuff. And at the end of the mine life, you get to the bottom, you reduce stuff, and you put that on top. So you put the whole pile upside down, and things get pretty nasty. Except the good news is that in the saprolite, the oxidized stuff, you can have up to 1,000 or over 1,000 before you really exceed that IC guideline. So you can have over 1,000 ppm arsenic in your oxidized materials, and they don't really leach. The SFE, so the shake flask extraction, is a pretty aggressive leach, so we can be quite confident that that's not a problem. Now, the engineers love this because they can now design their waste dump to optimally buffer the arsenic, internally in the pile, and requiring minimal treatment at the end. Now, this next case study, last one, is a bit more applied, applied data analytics. So we'll rush through in the available time, but do come talk to me after if you still have questions. So here's where we actually applied a bit more of that wholesome data integration to come up with a comminution forecast in a porphyry copper deposit. Now, this is a bit of an extreme example. It's not always this big. Usually the trucking, hauling stuff component takes up a bit more energy. But the whole point here is that generally comminution can take up to 50% of your total energy at a mine site. Even if it's a little bit less, it's still very, very significant. So if you can say something, if you can forecast something about the energy required to crush, mill a rock, it can help you also schedule, blend, etc., etc. As we're mining lower and lower grades, we also try to, mill finer and finer. And you can see here, the finer milling you go, the more energy per unit, per ton is required to actually get to that really fine material. So going from, 10 millimeters to 1 millimeter, yeah, that's a reasonable increase. But from 1 to 0.1, now it's massive. So you need to really know what's really required. What is the optimal size distribution, grain size distribution there? So a little bit about comminution. Comminution means different things at different scales. So obviously, when we're blasting, we're dealing with a rock mass here. So the blast index is really a function of rock mass characteristics, the large scale stuff, the structures. So these are structures in the rock mass. Now we go to crushing. We're still dealing with smaller structures at a smaller scale. So we get the crushing work index, which we do with either cone or jaw crushers generally. When we go finer in our grinding, we're looking at the drop rate index, for instance, or A times V, or other proxies for comminution, or grinding energy required. Now it's becoming more a function of texture in the rock, right? We're dealing with this sort of centimeter scale material. We go further down to the ball and the rod mills, and we come to our bond work index. We're dealing with essentially, in most cases, individual mineral grains and their energy properties. So the closer we get here, the point here is that the closer we get down to the mineral grain, the more we're dealing with the mineral properties themselves, which are a function of the mineral composition. So essentially the geochemistry. Now, if we take this and we generate random forest models for the taking, in this case, UCS, which is the uniaxial compressive strength measurements, which are a reasonable estimate for fractional, at the blast scale, the drop rate index here, which obviously we have got fewer points because it's a more expensive test. And then the bond work index, we get pretty good results that tell us that we can be quite confident in our random forest model predicting the actual comminution parameters. Now, unfortunately, client asked us not to share what's on the axes here, but just to point out, the next step in the random forest analysis is that you can actually identify which are the best indicators. So of all the parameters you measured, which are the best indicators for each of these indices. So you can use those not only to identify, what the dependencies, but also to help cluster, to say, well, we'll take this top here of the top 10 or whatever number here that are significant predictors. And it turns out that these are actually the ones that are predicted, by feature engineering. So our calculated ratios and indices are generally stronger predictors of these. You can imagine an alteration index, something like that. They're stronger indicators than individual elements, for instance. So it's worth doing that feature engineering step. Unfortunately, you don't have time today to get into the depths of that. But the point is here, we can use those to now go and say, well, let's take those and cluster the data to help us find these comminution domains that each have different comminution characteristics. So you can see here the UCS, the predicted UCS drop rate index and the bond work index. And you see that they vary quite a lot between the different color groups. And yeah, I can get into details this over a beer with you about how to cluster your data in PackMaps. PackMap is a publicly available tool on the GitHub. So if you use Python, you can just download that. It's really a tool it's a bit like UMAP if you're familiar with that kind of data processing. It's a bit more true to the data, especially in the compositional data. So I'd recommend you look that up. Point here is that we have these comminution domains. They match with geological known domains, and we can assign predicted comminution parameters to them. So this allows, again, clients to schedule, stockpile, and blend if necessary to optimize their throughput and energy consumption. All right. Bit coming through everything. But to summarize, if we have and do the early and comprehensive material characterization from mapping and predicting and simulating downstream processes, we can really get better at forecasting total asset value, forecasting and reducing financial risks that are hidden, obviously, in these other risks. So operational risk, environmental risks. Get more realistic closure planning if you include your waste and tails. We're mining a lot more waste these days than we are mining ore. So it makes sense to also characterize that. And we're being pushed to do that anyway. So if we know upfront, if we know better what's in our mineral deposit, we can also communicate that better. So it helps with community engagement and buy-in from the people working around it. And it might also help you, get your permit organized more quickly. So why aren't we doing this yet everywhere? Really, it is the analytical data. So the quality of the analytical data has improved a lot over the last 30 or so years, but mostly it's the data analytics, are the ability to now take very large data sets and crunch them to great detail. That ability is relatively new. And I would encourage you all, if you have any young geos in your company interested in analytics, to really, send them on a Python course and get that. It's more important that you know the geology and learn your data than the other way around. Don't just hire someone from Silicon Valley for obvious reasons. But anyway, the point is geological knowledge still required to inform this process. But if you then apply the available data techniques, there's so much more we can do and should be doing. So with that, thank you very much.